I hope you can see my slide.
Yes.
Okay. The inventors on this particular body of work are Sang Han, who's from School of Engineering, Christos Christodoulou, who's the Dean of School of Engineering, Olga Lavrova, who used to be a faculty with us at engineering at UNM, but has since moved to New Mexico Tech and continues work in a similar field, and myself. So this is part of quite a well-funded effort. Around 2012, we got this NSF grant called SEPTET, which stands for Sustainable Energy Pathways Through Education and Technology. And it's a very unique grant in that not only does it focus on renewable sources of energy, it also talks about how you can communicate energy concepts to the public. So it funded art installations. So we worked with the School of Architecture to sort of show displays where you could get a feel for how much energy your house is consuming through colorful artifacts in your house like LEDs and such. It would also give you a good idea how much energy your house was generating. Also public installation of arts. And it was through this program that we started thinking about this particular invention, which I'll get to. The second award that funded quite a bit of work for this was the NSF Quest Engineering Research Center. So the NSF ERCs, or Engineering Research Centers, are crown jewels of the National Science Foundation. There are typically 10 of these in existence at any given time, tackling some of the nation's most critical issues. So this particular one was started in 2011 at Arizona State University as the lead, and UNM, Caltech, and in MIT were the co-leads or co-PIs on this. And the challenge that this particular ERC was looking at was the terawatt challenge, or to establish a terawatt of solar generation in the United States by the end of the program, which we've come pretty close to doing. It's been 10 years. The program just ended and has had quite a considerable list of achievements in the past 10 years. So the premise here is that, solar is perhaps the fastest growing source of energy, renewable energy or otherwise. And it really isn't solar that is holding us back. It's more the grid system that needs to catch up with solar. And photovoltaics being a commercial technology that scales very nicely with similar areas such as electronics, microprocessors, all based on silicon, you can expect a considerable cost reduction and availability in the world for silicon-based solar panels. And that has materialized in the past 10 years. The question is, if you're going to deploy so many panels in the world, there has to be something else that these panels are also useful for, right? Because, typically the sun rises 7 a.m., peaks at about 11, 12, and then sets at 5 or 6. So you have about 2 to 3 hours of maximum production in the middle of the day, and you have a tail that's growing in the beginning and then that's tapering off. And this is also not the length of the production varies from its seasons. It's a lot more in the summers and a lot less in the winters. And once the sun is not there, you have a huge installation of solar panels in the world that just sits idle, doing pretty much nothing. And the question that we asked ourselves was, with all of this silicon and all of this metallization that goes into it, glass, aluminum frames, electronics such as microinverters or proper inverters that are attached to these panels, there must be something else that we can also do with this so that we can utilize them 24/7 instead of just about 7 or 8 hours a day. And so that was the premise behind this invention. And the way we tackled it was, we said that since they're all semiconductor devices, they're all PN junctions, we could certainly devise thermophotovoltaics, which are photovoltaic devices that don't use the sun's spectrum to generate power, but rather would use thermal signatures from engines, from boilers, even hot concrete as it's cooling down in the evening, and convert that to electricity. Perhaps, in some applications with the widespread presence of RF waves, cell phone towers, Wi-Fi that are just ubiquitous now, you could potentially start harvesting those waves and start converting them to power as well, to power very specific devices. So the combination of all these ambient energy sources in an urban environment could power a whole generation of sensors, and specific applications. Perhaps not things that are a huge power drain, but little things that we come to expect, lights, sensors, things like that. So this is the energy production chart for the world. And you can see that the United States has held fairly flat for the past 2 decades at about 4,000 terawatts hours per year. And even a country like India hasn't grown that much, but really the production for much of the world has shifted to China. And you can see that in the amount of energy consumed by China. And it overtook the US somewhere around 2007 or 8 and hasn't looked back since. You can also see the energy consumption per country in the second map. And the dark blue is the highest energy consumption. And you can clearly see that United States and China are the two largest consumers of energy in the world. But if you look at it per person, you immediately notice that China drops quite significantly given its large population. And even a country like India drops quite significantly. And the major consumers are actually North America, Canada, US, Saudi Arabia, and Norway, of all places, right? So it's an interesting view. So the question is, how do we produce our energy? And you can see the chart to the right shows how global energy consumption is split by source. And predominantly, you still have non-renewable sources, coal, natural gas, to generate our energy. Solar is making a large impact and has become one of the cheapest sources of energy to install, along with wind energy, which is also catching up quite well. So the question really is, how much solar would we require to power the entire world? So how many panels, or how much area do you need to cover? And I didn't make this map up. This is actually a map that's used by quite a few people. Everybody likes to just deck New Mexico with solar panels to make the point. So if you covered New Mexico end to end with solar panels, just completely, so we would all be displaced, I guess. You can meet the world's energy needs without a problem. This one state with the sun it receives is enough. Okay, so clearly that is impractical. I mean, you don't need me to tell you that. You need a more distributed approach. You can't just stack all the solar panels in one place. For starters, it exacerbates the problem of the sun going up and down. So if you have all the panels in one place, you only produce energy when the sun is shining on that particular state. So a better approach and a more targeted approach would be to target large cities and have a distributed rooftop solar approach. And you can see some of the big cities. I've picked different examples. New York is a rather compact city, high population. So in New York, you'd have to cover 25% of the city area with solar panels to meet its energy. London is a much more of a sprawl. So despite having the same population as New York, you can get away with just 8.8% of London covered by solar panels, despite it being in a more unfavorable latitude for sunlight. But if you look at Phoenix, and actually if you look at Albuquerque, and I don't have the data for Albuquerque, but Phoenix and Albuquerque are larger. Phoenix, at least, is a pretty decent sized city, but it only needs 1.8% of its surface area to be covered by solar panels to get its energy needs. Which brings us to the question, how do we do it? So we used to just put solar panels in the roof, but now people are starting to go with building integrated PV. So these are some examples of where walls are becoming solar panels. Another example, I forget which railway station that is in Europe, but skylights have solar panels as well. So, you know, just getting a little solar here, a little solar there puts a huge dent in that city's energy consumption. And you can go city by city and start reducing humans' consumption on non-renewables. Now, so if that's the approach that the world is taking, which, and you'll have to take it from me that that's what it is taking, then we need to get more from our solar panels, which are now going to be found all over the city. So you can go with more efficiency, but the problem with more efficiency is you're limited by silicon. 25% is doable with cost constraints. Going higher is harder and makes it more expensive. So dollar per watt is a key metric. You can't make very expensive panels. So the other option that people have come up with is bifacial panels, where you can absorb from both the front and the back. So when you have a solar panel, the light bounces off buildings, diffuse light, and it gets absorbed in the backside, and you can boost the efficiency. And that is what made us think that perhaps integrating additional capabilities, like in this case, you have two panels, one in the front, one in the back, could perhaps increase the efficiency of our panels. And in particular, we were interested in the ambient sources of energy. We were not looking to make huge amounts of energy, but just sufficient energy in the evenings and the nights to keep some of the city's electronics and lights going. So this is not something that is to replace utility scale power sources. So this is the idea we came up with, where we had multiple layers. The top metal that you see acts as both the metallization for the solar cell, and it also acts as little antennas that can be reconfigured. This is Christos Christodoulou's work, where these antennas can be used for harvesting a broad band of RF energy. So if nothing else is going on, then it's night, the solar panel starts to absorb energy from radio sources, and that can be used to power a few devices. In the daytime, you need the solar cell, so that's the main device in the stack. And in the bottom, you have something called a thermophotovoltaic, which I explained, which uses heat signatures to convert black body radiation into electricity. Again, in a concrete jungle, there are plenty of hot surfaces, but also in addition to that, there are lots of thermal sources like engines, generators, boilers that are giving out black body radiation in the night that you can certainly make use of. The one other idea that we didn't include in the patent, but we probably should have, is vibration energy from roads and machines, which can also be used for converting to wasted energy to electric power. So one of the things I'll show you some results on that we've gotten some good results on this concept is the integration of a TPV, a thermophotovoltaic cell, below the solar panel. So in this case, we engineered a growth process of crystals where we would grow a narrow bandgap semiconductor called gallium antimonide, which consists of gallium and antimony atoms. And we integrate it on top of a different crystal called gallium arsenide, which is used for solar cells. It's wider bandgap. The little stitch mark you see at the interface is actually atoms being skipped. So it's a very unique growth mode that was fully developed at UNM, and we have additional patents on this growth mode as well. And it leads to very high quality crystals for both the gallium arsenide and gallium antimonide. So here is some of the proof of concept work that we've done. And you can actually see that in one case, we built a device that has a antimonide thermophotovoltaic pixel grown on top and on a gallium antimonide substrate, but we were also able to put it on a silicon solar cell substrate. So the back end, this pixel is absorbing heat. I shouldn't say heat, but rather black body radiation and generating power. And in the front end, during the daytime, it is just doing the traditional solar cell job of converting sunlight to energy. And we've gotten some pretty interesting results, and these are some of the latest results comparing state-of-the-art to UNM. The reason you see some of the values to be lesser than state-of-the-art is that anytime you introduce a third material, a different material on a silicon solar cell process, you will see a degradation in the silicon solar cell's performance, and that is something that has to be engineered and process optimized. So, okay, so I'm pretty close to being done. I think that there is a huge demand for such a technology in the sensors and IoT device. IoT stands for Internet of Things. These are objects that are constantly connected to the internet, and they're sending you data about the status of something. You know, is your refrigerator working all right? Is the stove on? Is your dog running out and lost somewhere? You know, things like that. And to actually have these types of sensors and IoT devices integrated with ambient energy generators could be very potentially very useful, because then you don't have to worry about plugging each of these devices in, and they can be located in standalone places. We are also looking into the possibility of gallium nitride integration with perhaps solar panels in the backside, so that if something is a panel in the day, it can then be operated as a light emitter in the night, where it is giving you some illumination applications. You can always run a solar panel in forward bias and it becomes a LED. The only problem is silicon emits very poorly and emits in the infrared, so you can't see it. There's a bunch of other applications for it, such as scene illumination, where you have night vision requirements, where you can use such a technology. And I made this point already. So where we are right now, we have a proof of concept with antimonide TPVs on silicon and gallium arsenide. We also have RF devices that are capable of harvesting energy. We still haven't managed to put them on the solar cell and use them as both a solar cell contact and a RF harvester. That is yet to be done. And we are currently investigating several potential applications where this technology could be of use. Specifically, we are focusing on Internet of Things devices. So that was my presentation. Thanks a lot.
Great. Thank you, Dr. Balakrishnan.